Hello, we'll just wait for 10 minutes and then we'll start. Okay. Hello everyone. I guess today also will be just doing this session on my own. So this is week 10 and we are like almost 2 weeks ahead. So we'll be done in next 2 weeks and then we'll finally have your exam and everything will be done. So just from the introduction, I'm Jagriti, PhD scholar at IIT Gandhinagar. I'm working with Professor Karla Shekhar in the Muse Lab. My work is more on quantitative ultrasound for soft tissue characterization. So here, I'm the PMRFTA for this NPTEL course, which Professor Shubha Indra is taking. That's Techniques of Material Characterization. Okay, and what we are supposed to do is like we'll skim through the lecture week of last week, and then I'll show you the assignments for the current week from last year, so that you can solve the assignments for this year. Okay. So it's like people who feel that I'm going too fast, you can always go down and slow down the video. Of course, I'll try to be a little bit slower whenever I do the. Okay, so we'll just skim through and I'll just show you which all things are important and you need to consider having a look at whenever you are doing and solving your examples. Of course, your concepts and theory will come as and when you read the text and that to be by yourself, but not just going through this lectures. Both of us TAs are trying to solve the questions for you, but only solving questions won't only help. It's also, of course, it would help, but it's only 50% of the final exam. You'll also need to come, it's like you'll have you need to have a concrete background proof in your the theory concepts should also be very strong. Okay. So here, the concepts that we'll be covering is first one, the compositional analysis using. Oh, 2 minutes. 2 minutes, 2 minutes. Yeah, so sorry. So I had to do a booking for the experiment that I'll have later on. So only that's some glitch. Okay, so what we'll be looking at this week is this compositional analysis using backscattered signal, how people do mix them and how they get the elemental composition information from it. Then the inventor X-rays, electromagnetic radiation, and continuous X-ray spectrum. Of course, history is not at all. It's like you shouldn't memorize it, but of course, it's always good to know that who was the first person to come up with, how did he come up with it, and so that you can always back up your principles against some history and you have an idea to it. Okay. So yeah, this thing we saw last week also that the compositional analysis using backscattered signal. So what happened in there is that the area of the compositional interest would be first identified by backscattered imaging. Now you know it comes from the deep in the micron level depth of electrons, right? Backscattered electrons, and the phase compositions are then determined by doing some spot analysis of the X-ray signal of the characteristic signals. Okay. So it's possible to obtain quantitative compositional information by measuring the intensity of the backscattered signal from the phase of interest, or by comparing it to the standard element, or using atomic number versus eta relationships to compare the atomic number of that particular phase. So you have this linear, quadratic, and cubic relationship there. Okay, now here's how they have shown that how you can compare the spatial resolution, and with respect to it, how you compare or analyze the phases of all different atomic numbers using X-rays, which is not even a very easy task to do. But of course, uh, um, well, it does give you some information in context to your elemental composition. But there are disadvantages that great care must be taken to exclude the other forms of contrast there, such as if you have some topographic information which is involved, so then the results won't be that reliable. Okay, now when you have a secondary electron image that is from very like giving information of you about the morphology, and then you have something as backscattered electron image that's giving information about the topology. If you sum them both together, like you take one contrast of one, so it's like now everything is from the one sample, right? And now that sample represents 100%. If you're subtracting one, let it be x, another can be 100 minus x or 1 minus x. So if you multiply the pixels for both of them, you get the ratio of the image will contain the ratio of the intensities, how much secondary electron images are there, and how much backscattered electron information is there. So you what you get is like now we have splitted them. Now if we say that okay, there are equal number of information, then the ratio would be half of it, right? Then comes X-ray. Now, X-ray, the first time I read about X-ray was when I was doing this medical imaging course when I was in my bachelor's. And then we heard for this person that, okay, they were discovered in 1895. Air's not necessary, but the German physicist is necessary because he was Röntgen, and he was named so because their nature was unknown at the time. When the photo that you see over here is his wife's photo with the ring that the wedding ring that they have had, and that time it was given that okay, unlike the ordinary light, these rays are invisible, you cannot see them, but they are ionizing radiation, so can hurt us, and if prolonged exposures are provided, and they travel in straight lines, are affected by the photographic film in the same way as that of light is affected. On the other hand, they are much more penetrating that, and that of the light can go through us and could easily pass through the human body, wood, more thicker pieces of the metal, and other opaque objects. By placing the source of X-rays on one side of the object and a film on the other side of the object, you can directly map it or project it, and hence you can see that okay, how that radiograph has been made. The lens dense proportions of the object will allow you to have a greater proportion of X-rays to pass through. That means that it has not attenuated enough, it's not lost enough, so you get almost all of the energy. Then compared to a more dense material, well, it will have some absorption also. Now, in this way, there's a point of fracture in a broken bone, or a position of the crack in a metal can also be located in that case, because you'll have something as the differences in the medium, which will give you change in impedance mismatch. Now, almost immediately put to use by physicians and somewhat later by engineers who wish to have studied the internal structure of those opaque objects, which are not electron transparent, right? And in 1912, the phenomenon of electron X-ray diffraction by crystals was also discovered. And then through that, they can see the fine structure of the matter too. Right, so radiography. So nowadays you have this X-ray tomography, or you have this microcity. So exam, all of these instruments will give you the X-ray characteristics of your material, and then you can resolve the material to finer dimensions. It can also reveal the details up to this sizes. So now this is like 10 raised to negative 8 centimeter of atomic sizes. Okay, so that's almost like an angstrom that what you're trying to see over there. Okay. Now, these are electromagnetic radiation, we know because how they fall into the spectra, and they also have the exactly same nature as that of the light, but we have very shorter wavelength. Okay, so they are electromagnetic radiation of the same nature as that of light, but have a shorter wavelength, and how their wavelength rise to and how their wavelength is compared to visible light, that's also here. X-rays occupy the region in between this gamma and then this ultraviolet rays in the complete electromagnetic spectrum. So there your X-rays are there. Okay, after that, your different frequencies start coming. After that, your microscope frequencies are also there. Okay. So now we know about electromagnetic radiation and how X-rays were invented. Now we need to see that how they travel through and what happens when they travel, right? So if you have a monochromatic beam of X-rays, that's nothing but what monochromatic means, one signal wavelength. So if you have a single wavelength that's traveling in X direction with an electric field, let's say E in the Y direction, that's at right angle to this, then a magnetic field will be generated in Z direction, right? So if you take cross product of both of them, you'll eventually go into the Z direction. Now, if your energy is defined to xy plane as it travels along, then it is said to be as plane polarized. So it's only proportional to that particular plane. So it's isotropic in that plane, right? Now, in a completely unpolarized field, we can assume that all direction in the yz plane. So if it's unpolarized, E, the energy that you have, electric field that you have, and hence the H can assume it in all directions. That's it in the yz planes. Okay. Hmm. And then if you have in a plane polarized wave, so this is not constant, but it will vary as that of time. It will go maximum in the positive y direction and minimum into the negative y direction, back again, and then at x equals to 0. At any instant of time, we say if t equals to 0, it will vary at the same fashion as with respect to distance as x does. Okay, so if both variation, we do assume if they are a sinusoidal. So if you see if both variation of x, t with a fixed value of x or x with a fixed value of t, then you can define the electric field as that of sinusoidal. Okay, now if we say that this is a beam of X-rays which carry some energy, the energy is being have to has a rate of flow and through a unit area, then it is nothing but called as intensity that's proportional to your amplitude. So how much it is going through with respect to one particular cross-sectional area. Okay, so you have this continuous spectras. So what do you see from these continuous spectra? So well, you have two different types of spectras. One are due to Bremsstrahlung and another are due to characteristic X-rays. The one that you are seeing over here are due to characteristic X-rays, or I guess no, it's due to Bremsstrahlung, I suppose, but we'll see. Okay, because you have a sharp peak and later it continues. So an accelerated electrical charge will radiate energy. The charge will continuously oscillate about some mean position, act as an excellent source of magnetic radiation. The frequency is nothing but frequency of the oscillator. X-rays are produced when any electrical charged particle of sufficient energy is rapidly decelerated. Electrons are used for this purpose, radiation being produced in the tube with the source of electron and metal electrodes for it to converge through. Now, high voltage is maintained across these two electrodes and some tens and thousands of volts and rapidly draws the electrons from the anode to the target or when they strike with higher velocity. When they strike, the X-rays are produced at that point and nothing but they radiate in all directions, right? So that is how it works. I hope you are getting an idea that, okay, how the system would be. We'll also see eventually how the electron gun looks like or how the assembly in between. So you have two electrodes and then how from where's the source of electron and how they all converge together. So most of the kinetic energy that is striking is converted into heat, but less than 1% is transformed into your X-rays. So rays are coming from the target are found to have consist of a mixture of different wavelengths, but now this is only monochromatic and variation of intensity is also found to be dependent on the tube voltage. Of course, how much voltage you are trying to get will depend on the number of electrons that will pass through. So intensity is zero up to a certain wavelength, that short wavelength limit, and will increase rapidly to maxima and then will decrease with no sharp limit along the wavelength side. The radiation that is represented by such curves is called as heterochromatic if it has multiple wavelengths into it, or breaking radiation because it is caused due to the electron deceleration effect. Okay, so then similarly, if we compute it, you'll have C is equals to what is your See, speed of sound is nothing but a sort, in this case, speed of light, sorry. So that is nothing but your frequency times your wavelength. Now, if you want to find wavelength, that's your speed divided by your frequency. Now, what's your another is like you replace it. So it would be, it's C by lambda. Sorry. It would be HC, so you convert it back. So if you get, you know the electric field as electron volt, that you can also represent it as H mu max, and then you can also add it. So you mu max can be written as H by EV. So you just replace those terms over there, and there you go have an equation of the relationship in between the electron volt, the volts, and the wavelengths that you have, right? So yeah, so that's some relationship in between frequencies that we saw. And this is the total intensity across length that we are trying to see. So it always has a proportionality constant there. Okay, and now it's not about the constant here because It must have been derived through some empirical derivations. But one thing to note over here is that your target material would always affect your intensity. It won't affect the wavelength of the continuous distribution, but it will affect the value, the quantified value of your intensity on which particular material it's been going through. Okay. I hope that was clear. Now, before starting another session, I like another lecture. I like to stop here, have a pause because we have already done two in a row. I didn't realize that. Sorry. I'll just pause here for a bit. We'll wait for 5 minutes and then we'll start this one. Okay? I hope that's okay with all of you. I guess we can continue now. I even don't see anyone join now. But okay. So the next one is characteristic spectrum, the radiation and production of X-rays. So of course, that one what we saw was brainstorm because that's a continuous spectrum. Okay. Now what we see over here that while the continuous spectra is caused by the rapid deceleration of the electron of the target, by the target, the origin of this lies in the atom of the target in the anode itself. So if you consider an atom which has like k element shells, then you'll also have number of electrons lying in those shells. Okay. So if one of the electrons that's bombarded the target will have sufficient kinetic energy, it will knock the electron out of that particular shell, will leave the atom in an excited high energy state. Now some other electron, outer electron will immediately go and it will fall into that particular vacancy at that shell. So in this particular process, it will emit very high energy, and that high energy, once the atom is again in normal state, it's okay. But now something that we always read previously was that that particular electron is called as what? That's an agar electron or ogar electron or agar electron, howsoever you call it. Okay. So the K shell vacancy may be filled up by another electron from some outer shell, thus giving a rise to this all K series. So you have K alpha, beta, gamma, those shells you have. Okay, so K alpha and K beta lines result from filling of the shell vacancy by an electron from the L or M shells, and then alpha 1 and alpha 2 are due to the electron transitions in between the orbitals, that is S and P, in the L shell towards a vacant K shell. It is possible people who are doing some like physical chemistry and stuff will also definitely understand this, but people who are not, it's fine. Just understand the concepts of auger electron, and it's definitely okay for you to understand that part only. Now, it's more probable that a K shell vacancy will be filled by an L electron than by an M electron because that's more far away. And the result is that the K shell will always be stronger than that of the K beta line. So it's very obvious. Okay, so again, you define the kinetic energy, half mv square for it, how much energy it needs to go out. And yeah, of course, that's it. So you just have to see the energy differences. So what we need to see is like just remember the concept, what's happening there. Okay. Then the next one here is the production of X-rays, absorption, mass absorption coefficient, and absorption edge. So we see the Bremsstrahlung one, we see the characteristic one, and we see how it different. So the spectrum of molybdenum at 35 kilovolts increase the voltage has shifted the continuous spectrum to still a shorter wavelength, increased intensities of the K lines relative to that of the continuous spectrum, but they have not changed their wavelengths. The wavelengths are essentially the same, right? What happens there is we'll see exactly what's the difference there. So if you see the intensity of the characteristic line measured above the continuous spectra, this particular line depend both on the tube current and the amount by which the tube current exceeds the critical voltage for that K line. So there is some formula for the same where you have some proportionality constant, you have your current falling through it and the differences in the voltage which is exceeding above the critical voltage. So besides being very intense, these lines are also very narrow. So most of them are less than this angstrom. And the existence of the strong K alpha line is what makes it a great deal for the X-ray diffraction to possible, since many diffraction experiments make use of that of the single wavelength excitation, single wavelength radiations. Okay. So then comes your Moseley loss. So what does Moseley says? So the characteristic X-ray lines which were discovered by Bragg and systemized later by Moseley's. So the law gives us that the wavelength of any particular line is decreased as the atomic number of the emitter increases. So with this, I guess we have already seen previously that how wavelength is inversely proportional to the atomic number, and it's also inversely proportional to the difference in between the voltage and the atomic number, if you remember it correctly. So here what you see is it's nothing but square root of the frequency, which is proportional to this one constant, and then you have your atomic number also. So frequency and atomic number are directly proportional to each other, but your wavelength is inversely proportional to that of your atomic number. Hence, if one decreases, another one increases through the emitter. Now, the L lines are not always of the longer wavelengths. Alpha lines, the heavy materials will have the same as that of the K shell electrons of another material. Okay, so you just need to see that which one has particular material properties and characteristics there. Okay. Mm. Yeah, then we see production of X-rays. So what happens when are X-rays generated? So X-rays are produced whenever some high-speed electron will collide with a target, with a metal target, right? Now, what are the three necessities that you must have there? You should have a source of electron, something to accelerate, and something where it will go hit and then it will produce those radiations which will get distributed further. Okay. So since most of the kinetic energy is converted into heat, the later is always almost water cooled, because so that you don't have any melting there because it's so heated. So all tubes will contain two electrodes. It's like positive, negative, anode, cathode. One, both are your metals with few exceptions, the ground potential, those things. And at a high negative potential for those of orders this, so that your diffraction to occur there. Right, you always want them to go and bend and hence to produce those characteristic lines. So X-ray tubes may be divided into two basic parts. So first is your gas tube, where electrons are produced because of ionization of a small quantity of gas. Then you have your filamental tubes, in which the source of electron is placed or stored there in a hot filament. Okay, so any form of energy, if it goes and transmit, if it's being transmitted, it hits and then passes by, will undergo absorption, scattering, and what do you call it? Attenuation. Right. So these three things, whenever you have the so similar, if it's light or sound, we have I guess previously also discussed the same. So when X-rays encounter any form of matter, they are partly transmitted and partly absorbed. Electronic transitions in atoms occur not only in the form of interaction between electron and atom, but also due to the interaction in between X-rays and atoms. Okay, so how it comes? So here also, if you see the intensity with respect to intensity, if we are transmitting I naught, something that we get after decreased is I. Here is a trend they have also tried showing. So if you remember de Broglie's relationship, de Broglie's wavelength, or if you remember Beer-Lambert's law, how they both came to be. So this one is also very easier for you to follow through. So similarly, so this is nothing but it decreases exponentially. Okay. So what happens here? If you have a fractional decrease in intensity of an X-ray beam as it passes through a homogeneous material, which is proportional to how much distance is traveled to. So the loss, the attenuation that you have in such you represented by mu, and then it's proportional to the distance that it has traveled to, and that's a fractional intensity it is proportional to. Okay, so this is the linear absorption coefficient. It's dependent on the material characteristic, also the density and the wavelength. So if you have a mass or you have a mass density, both terms would be varied. There's only a factor of density in those cases. So on integration, what something you have is like this. Now, if you integrate this term, you'll have log here. If you take that log to the other side, you get exponential. So this is how it's written. Ix is I naught times E is to mu x. Okay. So it is also proportional to density. Divide by density multiplied by density. You just get a physical state of any material, whether it's a solid, liquid, or gas in such cases. So this particular coefficient, if it's just mu, it's your linear absorption or attenuation coefficient. When it's mu by rho, then it's your mass absorption coefficient, because now density is being considered into there. And what's density? Density is mass by volume. So your mass is also considered for that particular material for a given physical state of it. Okay. Now, if you, it also follows laws of addition with respect to the weight fractions of the elements. So you can always add all of those in between materials if you're trying to look at. Now, there are some relationship in between the absorption edge. It's not that important, but always remember that how your mass absorption coefficient is related to it. So your mass absorption coefficient is proportional to the cube of wavelength and cube of your atomic number. So thus this thing, there is no such basic like some theory behind it. So it's empirically derived. So shorter wavelengths X-rays are highly penetrating, that we know, and are termed hard. And while long wavelength X-rays are easily absorbed and are termed as soft. So if you have a shorter wavelength X-rays, they're highly penetrating. So it will go into hard X-rays, whereas the longer ones are the softer ones. Shorter are the harder ones, whereas longer are the softer ones. Okay. The ones which can easily be observed, ones which can interact and then will reflect back. Okay. Yeah, then you have absorption. So what happens? It's scattering, and then you have true absorption. So one will go. So there are two fractions that will always happen. One can be scattered back, one can be reflected back, one can get absorbed into the same material there itself. Okay, so this is also H mu where you see Hc by lambda. Then the Auger effect, from it will jump back from the higher state of atom to the lower state of atom from where it was released back, because you have now higher energy over there. So I guess that's it for this one. Anything, so we have anything else to look on this particular lecture? I'll give you 5 minutes. If you have any questions, you can let me know. If someone wants to join, they can also join between period, and then we'll start with the assignment questions, which is crucial here. Okay. Well, I guess we waited for a lot of time, so let's go for the assignments and we'll see that what questions are there for this week so that you can solve the current week's exam assignment solutions. Okay, so we have Moses' law, and we just saw that what Moses' laws tell us. That is it the frequency of the edge or the atomic number, or is it the wavelength of the characteristic emission or the atomic number, excitation voltage or the atomic number. So think for a minute and then it's like fix on your option, something like Kaun Banega Crorepati, and then we'll look at what's answer is. Your time starts now. Well, we won't do like that. Of course, the answer is first because we just saw that the wavelength is inversely proportional to the atomic number. So if it's inversely proportional to atomic number and wavelength is also indeed inversely proportional to frequency, so then both of them are directly proportional. So in essence, it states that, and we also saw that square root of mu is equals to your C and then difference in voltage, and then you have your wavelength, and then you have your atomic number right there. So of an X-ray spectral is directly proportional to the atomic number of the element, right? Then you have this. If you have, so that's the thing. So if you know one thing, you can eventually solve for two other things, right? So two X-ray tubes have identical targets, but tube A operates at just a voltage that's critical to VK for a K series, but tube E is just about VK. Right. So one is at just excitation voltage, one is something above it. So V minus VK, which is true about the X-ray spectra that is produced. Both will produce same, only tube A will produce, B will produce, neither of them will produce. So the answer is right there. So you have to be producing the ones that is having characteristic X-ray lines, which because we need the voltage which is exceeding the critical voltage. So hence it will create that sharp threshold effect for your characteristic X-ray lines, right? Then only your distillate electrons will go through and then only you'll have a brainstorming effect. Now, which of the following statement about X-ray filters is false? So let's say the K absorption edge should lie in between both of them. A filter can completely eliminate the K beta line. Increasing the thickness will decrease the ratio. Filters are often made of a material. So I guess the elemental, the K absorption edge should always lie in between both of them. But let's see. Oh no, that's not an option. So the answer is this. A filter can completely eliminate the K beta line from the transmitted beam. So X-ray filters work by preferentially absorbing certain wavelengths that we know from the incident X-rays more than others because we need to have a monochromatic wavelength. The ideal filter material should have an absorption edge that lies in between both of them. Well, oh, so the ideal one should lie in between both of them. That's what I also thought. But now what it's written that the filters will work preferably by eliminating absorbing one. Okay, so the ideal filter length. So what's asked to us? Okay. So an ideal filter should have the range in between both of them, but it will completely eliminate the other so that it gets the only single wavelength. Okay, so we were halfway there. Okay. Next, a copper target that has V equals 29 is used in an X-ray tube. The most suitable filter material for this setup would be which one? So if you have a nickel, zinc, which material do you want? You want an X-ray tube. So you want it to converge there. So you want it to accelerate the electrons fast through. So which one do you take? Should it be nickel, zinc, iron, or cobalt? Higher atomic number or lower atomic number? That's a question here, right? So you always need to have a one. Oh, the answer is nickel. Why? Because it's suitable for copper 2029 because the absorption edge lies in between K alpha and K beta for copper. Okay, so for this one, you need to have information about their energy levels. Okay, I don't know that's information, so that's why I wasn't able to, but you should know those things. I guess for only the elements which are generally used, okay, I guess that kind of questions won't be asked, but yeah, if they are asked, the probably the energy levels would be stated there. An X-ray tube with molybdenum target is operated at a voltage which is below the exciting voltage. So the spectra will contain what? Will it be a continuous spectrum or will it have a continuous spectrum of lines along with it or it will only have K alpha and K beta? Well, the answer is C. Why C? Because it has lower voltage, so it won't be able to excite it through. So hence because we need for generation of those characteristic x-rays we need specific threshold energy and that energy should exceed the and which should not be lower, so hence it will have a continuous x-ray spectrum to be generated. Then two different crystalline powders of the same material, we have A and B, are being analyzed using X-ray diffraction. Now powder A is finely ground whereas B is larger and coarser grains. Which of the following statements is true here? It's about the powder. So one is finely grounded, second has a larger coarser grain. So diffraction pattern of A will have a sharper peak than that of B. B will have sharper, both will produce identical, both will be weakly. Okay. So you have finely grounded, so you don't have any homogeneities there, but you have a larger and coarser grain, and you want diffraction to be produced there. I guess B would be having, yes. So B would be having sharper beats than that of this, because the finely grounded ones are the smaller crystallites, whereas X-ray is interacting with them. I don't think so you'll have enough diffraction at different angles. And then eventually it would be broadened at effect, and you won't get a specific wavelength effect that you need to have when you are characterizing your specimen using diffraction related effects. Okay. Now, Thomson's equation describes the intensity of the X-rays scattered by a single electron interaction with the X-ray photon in worlds as what? So, is it the charge, mass, distance? I guess it's everything. So, yeah. So, it depends on the charge, mass, the scattering distance, and how intensity decreases over time, the angle, polarization effects, everything. The polarization factor will arise because of what? Arises because the incident light is beam is polarized, or the scattered is polarized, or the incident beam is unpolarized, or the electrons are polarized. What's being polarized and what the factor actually represents? So the factor, everything is unpolarized, right? It does not has any one tendency to go here or there, because this is now for the fact that most X-ray sources produce an unpolarized radiation, non-ionizing radiation, what we just thought. This means that the electric field vectors of the X-ray photons are randomly located in any location, so dipoles don't have an exact location. When an unpolarized beam interacts with an atom, when it interacts and then when it scatters there, when it has some interaction there, then only it gets polarized and gets a direction, right? And after that, the angle of polarization, everything will depend on the scattering angle itself. Now, Compton scattering is characterized by what? So this, I guess, you have read in your physics class 10th, 11th also. So an increase in wavelength of the scattered radiation, decrease, no change, or the emission of the characteristic X-ray lines. Which one? So the answer for that is increase, because it will when the photon interacts with a loosely bound free electron. During this, the extra photon will transfer some of its energy to that electron, causing it to recoil it back. And the scattered photon now has lost some energy, has a low frequency, consequently low frequency, so a longer wavelength, so it can go back, and then the incident photon. So an increase in wavelength of the scattered radiation, right? The frequency reduces, energy reduces. Last question for the day. If we have an atomic scattering factor for an atom with Z electrons, it is equal to when what? The scattering atomic the atomic scattering factor F for an atom with Z electrons is equal to Z. Okay, so it remains as Z itself. When what? I guess you know the answer for this. When the angle is zero itself, right? When the angle is zero, because what we have, it's the amplitude of the waves which are scattered by an atom with Z electrons divided by the Z electrons. So now if you don't have in both are Z's, so the angle in between them is nothing. So scattering is done in the forward direction. So that's basically zero. Okay. So I guess we are done for today. And since no one has joined till now, I'll just thank everyone. And I hope you all go back to the YouTube links and have a look at the session. Probably have a look at the quick Q&As. If you have any questions, please post on the discussion forum and let us know if you had any doubts. Okay. Thanks. Thank you.